Hello everyone, welcome to the first topic of our discussion, that is special relativity. And this is very important for us because throughout the course we'll need to use the concepts of special relativity in all the cases, particularly in relativistic quantum mechanics, where we need to discuss the relativistic generalization of Schrödinger equation, and also in different areas of particle physics. So let's start. So imagine that we have a coordinate transformation that does not involve stretching. That means we can only either rotate the coordinate, rotate the axis, or we have the option of inverting the coordinate, So that's basically saying that x goes to minus x, or y goes to minus y, or z goes to minus z, or all of those. And if we do that, we notice that we're doing something. That is, if we have a position vector in a Cartesian coordinate, let's just say, then the norm or the length of a vector in that coordinate does not change. So that's just saying that if this is a vector r, then we denote that this r actually signifies the vector before the coordinate change, so before, and after the changing the coordinate we denote it by r prime. After, then of course we have the relationship that the magnitude of r would be equal to the magnitude of r prime. Now, since we're using Cartesian coordinate, we can write r as x I hat plus y j hat plus z k hat. But we can also write this in different notation. That is, we can write it as x1 e1 hat plus x2 e2 hat plus x3 e3 hat. And we can write this compactly by writing it using a summation sign that says the sum of x I e I hat. Now notice that here we have the same indices with x and the unit vector e, and so according to Einstein's summation convention we can simply lift off this summation sign and could simply write x I e I hat, and because there is the repetition of the same index in two places, we'll just simply presume that there is a sum. And in future we'll always use this convention unless been otherwise told, because it's a simply great use of notation and savior of time. We can also write R as a column matrix, that is x1, x2, x3, and the unit vectors is implicitly understood based on the position of the symbol. So this would correspond to E1, this would correspond to E2, this would correspond to E3. Now, the coordinate transformation we are talking about, as I have said earlier, can involve rotation, and inversion. So let me give you a quick example of both of these kind of coordinate transformation that does not involve changing the magnitude or the norm of a vector. So for example, if we have a coordinate, so this is x, this is y, and this is z. And we rotate the x-axis and y-axis with respect to z-axis by some angle phi. Then the coordinate transformation matrix would be like this. We have cosine phi, we have minus sine phi, then sine phi, cosine phi, 0, 0, 1, 0, 0. So this would denote rotation by the angle phi with respect to the axis z. And if we have transformed the coordinate by inverting the axis z, that means the axis goes in this direction, then the coordinate transformation matrix becomes simply 1, 1, minus 1. So notice that if I denote this by L rotation and this by L inversion, then the determinant of L rotation is simply 1, and the determinant of L inversion is simply -1. Now this is a very important characteristic. I'd like you to know what these two expressions mean. It means that whenever we have some sort of rotation that does not change the norm of the vector, that will involve this expression here, which basically says the determinant of that rotation should be 1. It doesn't have to be just the rotation with respect to z-axis. It can be rotation about any axis, and that will have the determinant 1. However, if we get the determinant -1, then there is a bit of problem, because that does not involve rotation. This is actually, as the nomenclature says, a discrete coordinate transformation, whereas rotation is said to be a continuous coordinate transformation. Now, you might notice that if we invert two axes, that is both y and z axis, then would invert a sign here, and then suddenly the determinant of this matrix becomes +1. And there's a reason for that, and the reason is a coordinate transformation that inverts the y-axis like this would actually be a continuous rotation from the initial coordinate alignments. However, if now we invert the x-axis too, then once again we invert the sign of this component, and now notice that the determinant of this inversion matrix changes again. So this one is again inversion that cannot be continuously transformed from the initial coordinate arrangement.